This is lesson 7. We'll be talking about the RS counter. The verilog code for this tutorial can be found at projectfpga.com/tcp. Select the receiver counter. This is the verilog code. I'll be implementing this in Logisim for this tutorial. So this is the receiver counter in Logisim. So this counter has three main counters in it. The first one is this RAM4, the delay CLC counter. This RAM5 is for the IFG counter, and this RAM16 is for the byte counter. So what is this delay CLC count? So there are situations whereby we want to delay this FCS. This is the FCS. We would like to delay this FCS. That is probably we are receiving more data than required. We are having more data than required. Then we have to delay that CLC error check so that we can have more time to receive more data. So this delay CLC counts 4 bytes. The delay waits. It used to wait for 4. The delay waits for 4 bytes to receive more input data. We're going to see what this count is being used for, but let's see how it's being incremented, how it's being reset, and how it's being set up. So for us to use this counter, we must set it to 1. Whenever it's 0, it means no, we can't use it whenever it's 0. We have to set it to 1. So this is where exactly it's being set to 1. This multiplexer sets it to 1. So whenever it's set to 1, it marks the beginning of the counting. So for it to count, this AND gate is what sets it to 1. Whenever this AND gate is on, it initializes it to 1. So for the AND gate to initialize it to 1, this must be set. That is, this is the delay CLC enable bit must be on. Then 2, it must be in the state SFD. So whenever it's in the state SFD, set it to 1 and start incrementing. Now this is where the incrementing occurs. This is the adder that does the incrementing. So for it to increment, this AND gate here must be on, and to turn on this AND gate, the condition that has to be met is 1. Again, this delay CLC enable has to be on again, and 2. This is the second condition. It must be at least equal to 1. That is why we set it to 1. If it's 0, it's not going to work. It's going to be idle. It's going to be latched. It must be at least equal to 1. This OR gate ensures that this output of this delay CLC is at least 1 for it to increment. So in a case whereby it's 0, it doesn't increment, and I've given conditions for it to increment, which is the condition that made it to be 1. It has to be enabled. Delay CLC enable has to be 1, and it has to be state SFD. So when it gets to state SFD, it starts counting. Then this comparator here is what we use this comparator here to reset. So this is it. This comparator compares it with the value 9. So whenever is equal to 9, it resets it to 0. That is, the delay CLC counts up to 9. But since it starts counting from 1, that means we assume it counts 8 times. And since we are receiving 8 neighbors, we are receiving 1 neighbor per count. Since we are receiving 4 bits at a time, that is 4 times 8, which is 32, which is 4 bytes of data. So the delay CLC delays for 4 bytes count. So it counts 8 times, allowing 4 bytes delay. So now we are going to see later tutorial. We'll see what we use this delay CLC, how we used it. Then the next counter, which is this IFG counter equal to 24 is the interframe gap, which we studied earlier. We used it in the last tutorial to move from the state SFD to receiving the actual state data. So let's see what increments it and what resets it. So now, to reset this interframe count gap counter, this is what is required. This OR gate here, that is two conditions. Either one is in state drop, that is the suspended state. Whenever is in state drop, that means the data reception has been suspended. So once you've already suspended the data reception, set it to 0 continuously. It's going to be in 0 throughout the while. It's going to be in this state drop. It's going to reset it and set it to 0 and wait until new data reception occurs. So or now this is a 3 input AND gate, or 1. Let's see the first condition for resetting it again. 1, it has to be in state SFD. It has to be in state SFD. That is the next condition to reset the IFG counter. Whenever it's in state SFD and the data is valid, that is MRDV is equal to 1, and the last is whenever MRSD is equal to D. And you know that whenever this condition means start data reception. In the last tutorial, these three conditions was what we use for data reception. That is, whenever is in the MRDV is 1 and is in state SFD, and immediately receives the MRSD is equal to D. That is when data reception starts. So whenever data reception starts, reset this IFG counter and start afresh. So let's see how the counter increments. What actually does incrementing? This is where the incrementing starts here. This is a 3 input AND gate. So the first condition for incrementing is, starting from the bottom, 1, it has to be in either of these states. So these are actually the normal states, the normal receiver states. So it means you should start counting this IFG whenever is in any of the receiver states. 1, then 2, whenever you are not resetting it. 2, then lastly whenever is equal to 24. When is equal to 24, this IFG counter equal 24 turns on, and at that point don't increment again. That is condition for incrementing. So long as it's not equal to 24 and you are not resetting it, that is the condition for reset is not met and is in any of the receiver states, keep incrementing it. Whenever it gets to 24, stop. That is, you keep incrementing it until it gets to 24. So here it's this comparator here. This comparator compares the value with 1/8. This 1/8 here, let's see, this 1/8 here, we'll write it. This is it. 1/8 in hexadecimal is equal to 24 in decimal. That is, whenever it counts, is equal to 24, turn it on. Now there is another condition again. This R_IFG is set from the register. Whenever it's on, it means ignore it. The RIFG signal comes from the register. So whenever you set it to 1, it means ignore this IFG count equal to 24. It sets it to be high, steady. It means that the IFG counter is okay. It doesn't check whether it has counted up to 24 or not. It sets it high, steadily. That is, this RIFG means ignore this counting procedure. It keeps it on steadily. So all this will no longer be considered whenever this RIFG is on. So now let's talk about the byte count. So this byte count, RAM 16, This is the main counter that counts the number of data we have received. So let's actually see what happens at this lower part first. This area, and see the signals that are being generated. All these are comparators. These are comparators. These are comparators. It compares the input of this byte count, that is the input that comes from this RAM 16, to certain values here. As you can see, it compares it to 5. If it's equal to 5, it sets byte count equal 5 high. Is it equal to 6? Byte count equals 6. Is it equal to 7? Is it equal to 0? It says the byte count equals 0. Is it equal to 1? Byte count equal 1. Is it equal to 2? Byte count equal 2. If it's greater than 2, it says this byte count greater than 2. If it's equal to 3, set this. If it's equal to 4, set this. If it's all 1, 1, 1, 1, that is FFF, then it's going to set what we call byte count max. Then there are two signals in the register model. The max FL, this comes from the register mod, max FL, and the huge enable. Huge enable means when you set huge enable, it means that you are allowing data size that are higher than the main set data size. That is, the maximum frame size you are expecting is set in this register called max FL. This is the register you are going to use this register to set the maximum size of data you are expecting. So, but if you don't want to use this max FL, as in you want it to be higher continuous, you can receive as high as possible, you can set this one, huge enable. Huge enable means any size have a huge number of frames. So, but if huge enable is not set and the byte count is higher than max FL, or whenever is equal than when is equal to this max FL, is going to set this bit high. And we used this bit already here in our last tutorial when we talked about the state machine. That is, we used it here, this byte count max. It means that you have exceeded the normal size of frame you are actually expecting. So this is when this signal is being generated. But assuming you set this huge enable to 1, that means this signal can never be set. You will keep receiving as long as possible until when the transmitting station decides to terminate the connection. That is, once you set this huge enable to 1, it keeps receiving as long as possible. But if not, you are going to set this max FL, the maximum frame size. So whenever the byte count counts equal this maximum frame size, this byte count frame signal comes on. So that is it about this lower part. Then let's talk about the byte count itself. The section that does the counting. So let's see what resets it. This is where it's being reset. What resets it, and then what sets it. So this is the adder that does the incrementing. But let's first of all see what does the resetting, what sets it to 0. So this AND gate here sets it to 0. So what are the conditions for this AND gate? One of the conditions is that 1, the MRXDV, that is, it must have valid data. It's going to get reset during a current data reception, that is when MRDV is on, that is towards the ending of a data reception probably. The first condition is MRDV, and we know that when MRSDV is on, it means that there is valid data. Then and now let's see the second condition. One is the MRSD is equal to D and is in state SFD. So whenever it is in state SFD and the MRSD is equal to D, and this MRSDV is on, this three condition is what sends it into the state data. That is when it starts receiving the actual data. That is, it has now moved from this SFD state. This is when it moves from SFD to receiving the actual data. The SFD, which is the frame delimiter, that is the condition for moving to receiving the actual data frame. So what it means, what it's trying to do here is that whenever you want to start receiving data, that is after the preamble stage and the SFD stage, reset this byte count and start counting the actual data reception. So that is what it's doing here. That is when it's in state SFD and MRS is equal to D and MRSDV is on, it means reset it and now start counting again. So once it resets and starts counting, it's now counting the actual data. It has passed the preamble stage and the SFD stage. It's now counting the actual data. So that is the first condition for resetting it. When it's time to count the actual data, reset it. Then the second condition is, let's see, when it reached the byte count max frame, that is when it has reached the maximum frame size is going to take and is in reception stage. You know, this state data is the state of data reception. State data means receiving data. So whenever it's in state data and it has reached the byte count max frame, reset it. That is, it has reached the maximum number of data it can receive, reset it. So these are two conditions for resetting this byte count. Now, what is the condition for incrementing? How does it count? How does it know that yes, I'm counting the data reception? So first condition is one, it must not, the condition for it must not be during the reset period. That is, this reset option is not here. That is, it must not be resetting. One. Then two, the MRSDV must be on. Then three, these four OR gates, these four input OR gates gives the four conditions for it. Now, first condition says one, it has to be in state idle and there is no data transmission going on. That is transmitting, no data transmission, is in state idle, and what again, it starts receiving reasonable data. That is MRDV is equal to 1, is not resetting to, then is in state idle and is not transmitting. So this first condition is a condition that starts data reception. That is, once this condition is met, it enters the state preamble stage. So whenever it's going to enter state preamble stage, start counting. That is what this condition is trying to tell you. Start incrementing whenever it enters the state preamble stage. Then this another condition is whenever it's in state preamble stage already, yes. Then the next condition is when it's in state SFD, continue counting. Then another condition is when it's in state data and this is multiple of 3. When it's in state data 1, then 2, it is not equal, it has not reached condition of 1 1 1 1. That is, it has not accumulated. FFFF, that is, this converter means, let's see it here. that is 1111. That is when it has saturated the counter, when everything is 111. It has not reached that stage when it's 111 and is still receiving data, that is state data. And the last condition is when the delay CLC, this means delay CLC. Let's go. So you can see it here. This is the delay CLC enable, and is not counting the delay CLC enable. That's what it means, is that doing the delay, when it's counting this delay CLC, when the delay CLC counter is on, it should not count this byte count. That is, the byte count should wait whenever the delay CLC is counting. The byte count, that is what this AND gate does. Whenever the delay CLC is counting, it should not be counting. So this is the condition for counting, for incrementing the byte count. So this is the condition for it. Now let's see why they call it byte count instead of neighbor count. You know, since the data is received neighbor by neighbor, it's supposed to be counting them neighbor. We are supposed to call it neighbor count, but it's referred to as byte count. This is because this state data which does data reception, it has two states. The first state receives the lower neighbor, while the second state receives the upper neighbor, but we only count one of the states. So that means when we are counting one out of two states, that means we are actually counting two states as one, and one of the states is for one neighbor, so the two states is for one byte. So that is why we call it byte count instead of neighbor count. The counter only recognizes one of the states. It doesn't record the counting here, only recognizes one of the states. It doesn't recognize the second state. So this is the state that is recognizes here. The other state is used for the reset, while this one is used for counting. So this is why we call it byte count. So with this explanation and the verilog code on this site, you'll be able to understand exactly what this receiver counter does. Please subscribe to my channel. Thank you.